it is recording. And I'm going to put a... Oh, the door is unlocked. Is it still unlocked? Oh, that's because Fox unlocked it. And my key cannot lock it back. So after this class, I'll have to go to the lab to get someone to lock it back. Yep.
That's strange that it's tied to a key to lock.
Right, because I have a black key which can only unlock a door for like 10 seconds. But if the door is already unlocked, it cannot lock it. Yeah, well, you know, that's what I think too, but you know, that's the way it is. All right.
So how did he custom to acquire a key to keep it unlocked?
I just lost mine. I had mine too. I lost mine, and they don't have any spares anymore. They don't have any blanks anymore, so they cannot make any new keys. So every key that we lose is gone completely.
You would think that they would have a way to order more.
No, the locks themselves are so old. They don't make those locks or keys anymore, and apparently have not been making those for a long time, because any existing stock of remaining keys are completely depleted already. Yeah. Alrighty. So I'm gonna get started. Okay. So I'll go ahead and get started with today's lecture. We are just basically kind of going through these slides one by one. Logic Sim is not going to be a very important page because it's just a place where you can download the tool Logic Sim. I can just open a new tab to go there, but there's not much to see. Okay, it's just a SourceForge site. Now, one thing about Logic Sim that is really nice is it has a lot of online help. Okay, has anyone installed Logic Sim? After the previous class. Okay, so if you go look under help, it even has its own tutorial to basically teach you how to do simple stuff, and it has a very good explanation of the components in its library as well. So Logic Sim is a really great learning tool from that perspective. If you have some basic idea of what the logic gate is and what the components are, it has a lot of possibility to help you understand, how computers work internally, at a low level. And we're going to use Logic Sim quite a bit in this class too. But before we get back to Logic Sim, we're going to talk about this slide here. It talks about binary numbers and how do you add and subtract when you're dealing with binary numbers. So this is kind of like the focus of today. We probably can get to half adding and also half adding and full adding. We might be able to get to subtraction too, maybe not. And today's lab is going to be a demonstration of how to use Linux on using just the CLI, the command line interface, to do everything that you used to do in Dev C++ or code blocks. Okay, how many people use code blocks or Dev C++, something like that in cisp310? Okay, so in this class we don't have anything like that. We just dropped all the way down to commands, just hand type all the commands in the CLI and do everything that way. Okay, it's not going to be a hard transition. It's the thing is you have to do it enough times to become proficient and just basically get used to it, just like everything else. Kind of like driving a stick shift, except there's no gear to grind in this case, no harm done. It's usually pretty safe. All right. So we'll go ahead and get started with binary numbers, addition, and subtraction. And this slide goes to one of my older notes. We can kind of tell it's an older note because it is written entirely using LaTeX instead of a web page, that I type inside Moodle. This is completely outside of Moodle. Okay. All right. So here is a slide that talks about binary numbers. How many people here feel comfortable doing base conversion from base 10 to base 2? Okay, so a pretty good number of people. So, but I will still kind of go ahead and talk about base conversion, because not everybody may know about base conversion. But before I talk about base conversion, let me start with something that you are all familiar with. So I'm going to use mousepad here, because this way everything is captured in the video, and we don't have to deal with the whiteboard. Okay. So let's say you have to come up with. I'm going to use a different number to do it in this class. So let's say you have to come up with a particular amount, okay, which is this much money. Using the more common U.S. currency bills and coins, how would you come up with this much money? That's easy. 14,875 pennies. That would do it. So, but what if I want you to use the least number of bills and coins? How would you do it? Okay, so most people know the answer, right? I mean, most people here can work at McDonald's or any store, a grocery store or 7-Eleven, and be able to come up with the right change. So the right change is $100 bill and two $20 bills, one $5 bill, and three $1 bills. I know there are $2 bills too, but it's not really common, so I'm not going to use it. And then we have half-dollar coins too, but not going to use it, so we'll use 3/4. Okay. Was that challenging? Was it hard? Were you able to do it in your head, like not having to write everything out on a piece of paper? Okay. Well, okay. You know base conversion already. In fact, you know more than what you need to do base conversion already. Okay? You're not convinced. Okay, let's check one thing. Okay, let's just write out all the common coins and bills and look at their values. A penny, nickel, dime, quarter, dollar bill, $5 bill, $10 bills, 20, 50, 100. Now we can go a little bit further, but these are the more common bills and coins that we use on a daily basis. Do you see any particular pattern that repeats and is consistent with the multiplier from one value to the next? Let's check. From here to here is 5. From here to here is 2. From here to here is 2.5. This is a 4, 5, 2, another 2, another 2.5, and another 2. I do not see any actual repeating pattern. Do you? Okay, now we can see certain multipliers are really popular. Okay, 2 is really popular. Even 2.5 appeared twice. But there's no real regularity whatsoever. And we know this stuff only because we have been using it for years. Okay? Now let's take a look at a different currency system. We can call that tax currency system. So with tax currency system, it goes like this. It starts with a $1/8. Okay, 0.125 is 1/8. Then it goes to a quarter. Then it goes to a $half, a $1, $2, $4, $8 bill, $16 bill, $32 bill, $64 bills, $1.28, and so on. You can probably guess, the next one is $2.56, $5.12, $10.24, and so on. First of all, do you see any regularity here? Do you see any pattern in this particular system? Everything is twice the one before, right? Including the fractional parts, okay? Okay, well, but that all by itself doesn't mean that it's going to be really useful. So let's see how we can come up with the same change using this particular system. So I'm just going to copy and paste it here so that we can see it. Okay, this is the amount that we want to come up with. What would you do first? Okay, because that's the largest amount that you can take off using, with this particular number. Okay, so we have 128, and after you take 128 out, you have 20.75 left. Okay. So with the remaining amount, which is $20.75, what is the next bill or coin that you will pick?
16.
16, all right. So with that $16, we have $4.75 left. And I'm just going to do it step by step here because I want to make sure that this is all recorded. Okay, right? Does that make sense? Because if you have $4.75 left, it makes sense to pick a $4 bill instead of two $2 bills or four $1 bills. Okay, because the $4 bill is the largest bill amount that is less than or equal to the amount that you want to specify. Okay. So after this, what do? Same approach. The next one is going to be a $half, right? And the last one is going to be a quarter. Is that working out okay? So given enough time, if we are to change the currency system to something like this overnight, it might take you maybe a week, maybe 2 weeks to really get used to it, but you will get used to it, right? It's not a big deal. So mentally, it's not really a big challenge. It's just, oh, okay, I'm more used to the old system, but the new system, I can deal with it. I just have to kind of slow down a little bit to get used to it. Okay. I don't see any binary numbers here. Do you? Let's see whether we can change it to a binary number. Okay. All right. What is 128 as a power of 2?
7.
2 to the power of 7. Okay. All right. So we'll say 2 to the power of 7. We got one of those. What about 16?
4.
2 to the power of 4. And 4 is 2. And half is -1. Yep. And a quarter is -2. Okay. Because it's 1 divided by 4. So that means it is 2 to the power of -2. I still don't see any binary numbers here. Okay. Now, this is the magical step. This is how we actually get to binary numbers. In binary, when you're using base 2, 2 to the power of 7 is going to be represented by what? 1 followed by 7 zeros. Okay, very good. Okay. So it's 1 followed by 7 zeros. And I'm going to use a 2 in parentheses to mean this is a base 2 number. In other words, we are not talking about 10 million here. We're talking about 1 followed by 7 zeros in base 2. Is that okay? Sort of? Okay. And I can come back to explain this one a little bit too. Just hold on a second. And 2 to the power of 4 is 1 followed by 4 zeros in base 2. In other words, whatever you raise 2 to the power of is the number of zeros after a 1 when we are dealing with a power of 2. So the next one is just 1 0 0 because 2 to the power of 2 has 2 zeros. The next one is -1. Okay, the power is -1. How do we do that? Sorry? Yep, we use a point to separate the non-negative power to the negative power. So when we are on the negative power, this is a 0.1 in base 2. And then we have the other one, which is 0.01, in base 2. Okay, not everyone is really convinced about this part here. So we'll just kind of let it sit, and we'll go back to base 10 numbers where we are all familiar with. As a base 10 number, tell me what is this value? 518, right? I mean, are you kidding me? This is like a college level class and we are talking about what is that number. Okay, but let's go ahead and rewrite this number a little bit. Okay, 518, what is the 5 really specifying? We have 5 100s, right? The 1 is specifying the number of 10s, and the 8 is specifying the number of 1s. Well, still, this is college, we really should not be talking about stuff like that. What is 100? Is 100 a power of 10, which is the base of a base 10 number? Yeah, okay, so it's 5 times 10 to the power of 2. plus 1 times 10 to the power of 1 plus 8 times 10 to the power of 0. Okay. Wow. Even though this is something that we have known all along, now we understand what a number really is. So every digit of a number is really just indicating the quantity of a particular power of the base that you choose to use. So when we're dealing with base 10, in this case, 500 is indicating that we have 5 of the hundreds, or 5 of the 10 to the power of 2. Is that making any sense? And that's why we can change the base from base 10 to base 2. Because in base 2, it is still following the same rules. Okay? The number of zeros after the 1 specifies which power of 2 we are dealing with. And this digit is specifying how many of those do we need. In base 2, you either have 0 or 1 of any power of 2. Because in base 2, you only have 2 alternatives per digit. And those are 0 and 1. Okay? This is one thing that most people do not get, because in base 10, we have how many digits? How many? 10. We got 10 digits, and they go from 0 to 9. So the value, the quantity of 10 requires how many digits to represent? 2 digits. Okay, so you got to remember that part. Okay, well, I still cannot see why this is a base 2 number. Well, the next step is really just to do the addition. Now, when you're adding 1 followed by 7 zeros to 1 followed by 4 zeros, I don't care which base you're dealing with, you will still end up with 1, 0, 0, 1, and then 4 zeros here. But I can do the same thing with all the other ones. So I'm just going to be quick and deal with that. That's 148.75 in binary. That's base conversion. Do we have any questions about the principle, the theory of how values or quantities are represented by numbers? Question? Well, I have a question. 148.75 is 148.75, and it should always be 148.75. How can it possibly be 100101000.11 and be representing the same quantity? I actually extended the notes from the other day a little bit. Actually, okay, sorry about my disorganization because I forgot that I did not finish everything from the previous lecture. There's a little bit of good stuff there too. Let's see, where am I? Low-level mechanisms and representation. 2 things, okay? We got 2 things going on here. The first one is I actually fixed the gates. So remember last time I discovered that I was describing this circuit incorrectly as a NOR gate. It's actually a NAND gate, a negated conjunction. Do you guys still remember that part? Yep, okay. And so I fixed all of that stuff and changed it to a NAND gate already. Yep.
I think you missed a section.
I missed a section?
I think so.
There was one more before the diagram.
I can scroll down. A little bit more. Yeah, more down. More down. You go down. There's another diagram, isn't there?
It's on the top. It's above the diagram.
Yeah.
Above the diagram. Say again?
It still shows how it's go up. The beginning when you showed us the diagram for the
Okay.
NAND gate.
More control of that.
How's that?
Yeah, there's still.
Oh, okay. Yep, you're right. Search is quick, right? I mean, that's great. Okay, so I'll remember to change that also. But this is supposed to be a NAND also. Thank you. Okay, but the point is, we can represent any type of gate using a NAND gate in this case. We can transform a NAND gate, or by using multiple NAND gates, we can simulate any other type of gates. So that part is all done. We kind of talked about this part last time. Did we finish all of this stuff last time? I think we did. We talked about De Morgan's law. Yep. So that's basically redoing everything, and come up with this one. No, not this one, but this one to represent a OR gate.
Yeah, we talked about it. We didn't show that.
Yeah, we haven't done that.
And then we didn't talk about the end block.
Okay, so we'll go ahead and get back to this one then. Sorry about that. Because I'm teaching 440 also on today, and we were kind of talking about that too, so sometimes I get a little bit cross-wired and forget where I was with this class. Okay, all right, so let's go back and rewind everything to just a NAND gate. Okay, so this is a good place to start. So the NOR 2 is supposed to be NAND 2, okay? It's a negated AND gate. Because high and high is supposed to be high, but in this case, the output is a low. High and low is supposed to be low. In this case, it's high, so it's the inverted or negated AND gate in this case. So are there any questions about why this truth table is telling us the circuit that we were talking about is a NAND gate? Yep, go ahead.
So how it shows like a low and low is a high. So when I watched that video, I didn't get that part. So if it's a low, if we get low and low, why it shows a high there?
Because it's negated. That's why it's a NAND gate and not an AND gate. Because a NAND gate means it's a negated. The output is negated.
But it shows the NOR on the top. So
You mean this one?
it shows NOR on the top, NOR to gate.
Yeah, because I forgot to change it. All right, you know what? I'm gonna fix it now. Okay, so sorry about all the scrolling. I hope no one is getting motion sickness. All right, I'm gonna change it.
Just do it find and replace.
Yeah, it doesn't have search and replace. Plus, I don't want to find and replace every single one. I just wanted to kind of give it. I wanted to give me a clue of where I'm supposed to fix, but not automatically do it. So this is a NAND gate. And 2. And this 2, this 2 refers to the number of inputs, by the way. So that's why it's called a NAND 2, because you can use more gates or more transistors to make a NAND 3, NAND 4, and so on.
You wouldn't necessarily, we essentially proved that a NAND gate with only one input is an AND gate. You wouldn't actually, you would never have a NAND one, right?
A NAND one is just a negation.
Yeah, that's what I'm saying, just
right.
like AND.
Yep. But the point is, but your point is interesting because the way they make a negation gate, just a NOT gate, is really similar to the NAND gate that we have, except you only have T1 instead of T1 and T2, and you only have T3 instead of T3 and T4.
Okay.
So if you take out T2 completely and replace T4 with a straight line, then you have a negation gate.
Okay.
Just straight negation. It doesn't do any type of actual logical function besides that. Okay. And I think we got it, right? Okay, I think we got it. Remember to save in this way so we can get back to where we were. So once again, scroll all the way here. All right. Okay, so are there any questions about this truth table? Why this is called a negated AND gate? It's just like a regular AND gate, except the output is flipped. Okay, it is negated. And this is a mighty gate because we can use this to implement any of the other logic gates that we are familiar with. The first one is a negation, just a straight negation. Now this is how we represent a NAND gate. If you look at, it's just easier for me to point out here and see. If you don't look at this little bubble here, just look at this portion. That's the symbol of a regular AND conjunction gate. Okay. This little bubble means the output is negated. So when you combine the AND gate and a bubble, it becomes a NAND gate. So by connecting both of the inputs to the NAND gate to the same connection to the input, it becomes just a negation. Does that make any sense?
So it's just without the bubble, that'd be an AND gate.
Without the bubble, if you just look at this portion, this is that's the symbol of a AND gate. Yep. There was another AND. Sorry? Okay. Yep.
That's a negation with the x1 and the x1 on both sides.
There's just both called x1. This is the input, and that's the output.
Yeah. That would be 0, x0, x1.
No, that's just name of that's a label of the output.
Oh, so okay.
It's just a label. It has no particular meaning. Okay. But if you're not convinced that this is really just negation, guess what? We can use a truth table to do it. So once again, we can use a truth table. You know, the input is x, and we can call the output y. Okay. In this case, how many inputs do we have? One single input. So one single independent input. So in this class, I use 0 to mean false and 1 to mean true. If the input is 0, then both inputs into the NAND gate will be 0, right? And so okay, let me just go in 1 and then input 2. So in this case, because these three lines are actually tied, right? The pin and both inputs into the NAND gate, they're basically the same node, electrically speaking, so they're all zeros. What is the negation of in 1 and in 2 in this case? 0 and 0 is 0, not 0 is 1, right? What if x is 1? When x is 1, the other 2 points will also be 1 because all 3 points are connected to the same node electrically. And so we have 1 and 1 being 1, not 1 is a 0. Okay? So now what you can do is to say, I don't really care about all the stuff that happens in between. So ignore this portion, just ignore this portion completely. If you look at the input, which is x, and you look at the actual output, the output is the negation of the input. And that's proof that if I connect the circuit this way, I have just a regular negation. It has no other function than that.
And then goes to x1, so it's the circle, meaning it's a different value, or
The circle,
So there's a
I see what you mean. You mean this circle here.
yeah.
In logic sim, if a pin appears as a circle, it is an output pin. If a pin appears as a square, it is an input pin.
But if they're both x1, how is it negated? They both it looks like
X1. Ignore the X1.
Yeah.
That's
The
just the
X1 is
name.
just a label.
Oh,
Yeah,
okay.
it's just a label.
Arbitrary.
Yeah.
Okay.
Yeah. That's a good point. It's just I forgot that they are changed the label of the pins. Yep. Right. So we have negation coming out of NAND. So we use one single NAND gate to implement a negation. The next one is OR, okay, disjunction, and that's when it is handy to use the Morgan's law. So with the Morgan's law, okay, the Morgan's law, I think I kind of explained that one last time too. So with the Morgan's law, I can establish the equivalency of these expressions. And so the bottom line is, with this expression, this is as an original expression, A or B, I can translate that into this big mess here. And the way I can prove that they are really equivalent is using a truth table again. Okay? So A and B are independent variables. A can be 0, B can be 0 and 1, while A is 0 or 1. If I work out all 4 rows, if I can establish that on each row, the value that I get out of this expression and the value that I get out of this really kind of complicated expression, if they are the same on every single row, then I have established that the two expressions are really the same. They are equivalent. And that's something that we did last time. If you're not convinced, You can also come up with your own truth table to convince yourself that these two expressions are actually the same. So the next question is, why do we go through all this trouble? Something that is so simple, A or B, why do we want to re-express that as the negation of the conjunction of the negation of A and the negation of B? Well, because sometimes you only have NAND gates to play with. So that's why we have to do the translation. Now we know that this one only involves NAND gates, because from the previous one we know that we can do negation, right? Negation is just tying both inputs of a NAND gate to the same input. So we can handle this one too. What about this? Well, this is a AND, but this AND also is has a negation right after that. In other words, that combines to a NAND gate also. And that's why with this expression, I can now implement it using only NAND gates. And the way they hook up would be like this. So kind of imagine this x1 as A, this one as B, and this is the entire expression. So we are basically re-expressing the same thing, except this time I'm using NAND gates to make up the entire expression. Is everybody kind of convinced that that's doing the same thing? The schematic of the gates is representing exactly the same thing as the written math equations. Is that okay? Okay. That is okay. We'll move on to the last one, which is kind of easy because the last one is the non-negated conjunction, not disjunction. I forgot to fix that one too. Okay, so just kind of imagine this as conjunction, not disjunction. So the way we do this is we have a regular NAND gate, and then we have a negation after that. So that will turn a NAND basically back into a regular AND gate. And that's why we can now implement negation, disjunction, and conjunction using only NAND gates. Yep.
Okay, so just for stuffs and giggles, how would you implement like an XOR gate?
An exclusive OR?
Yeah.
That's a good question. Let's do it as an exercise. Okay. How do we implement an exclusive OR gate? That's the question. Okay. So the first thing you have to do is to express exclusive OR not only as an operator, express it using negation, conjunction, or disjunction. Because we know how to translate those into NAND, right? So if you can express exclusive OR as a combination of negation, disjunction, or conjunction, then we're good. Okay. So let's go ahead and do this.
Well, yeah, let's say if we write the truth table first.
Right. You want to, well, starting with the truth table would be a good step to start. Okay. So let's go ahead and do this. We have two independent inputs called A and B, and we want to go by the truth table by the definition of exclusive OR. Zero exclusive OR 0 is
Zero. No.
yes.
Yeah.
0 exclusive OR 1 is 1. 1 exclusive OR 0 is 1. 1 exclusive OR 1 is 0. Okay, great. Now that we know how exclusive OR itself is defined, the next thing we want to do is to say, can we express exclusive OR using a combination of the other logical operators? Okay, so I'm going to say, blah, blah, or blah, blah, okay? So A exclusive of B is really the same thing as something or something else. Because we know that there are only two rows where the output of exclusive OR is a 1. So I will use one expression to handle the first one, and I'll use the other expression to handle the other one. And the two expressions will be joined by an OR because I want the output to be 1 in those two cases. Is that okay? All right. So getting back to here, if A is 0 and B is 1, what is one way to make sure that this will give me an output of a 1? But at the same time, I want this one not to give me, the other cases not to give me a 1. So I only want to have a 1 if and only if A is 0 and B is 1. how about something like this? Not A and B. Would that work? That would work, right? In other words, if I just look at not A and B, and I plug in A being 0 and B being 1, this will give me a 1. And all of the other values will give me zeros. Okay, that's good. That's okay, because I can handle all of the other cases using this expression here. I just need this expression to handle one particular row of the truth table. But once we know how to handle the first row, or the first row that has a result of a 1, we kind of know how to handle the other one because it's kind of symmetric. So the other one is just A and not B.
Oh, so it's the disjunction.
The conjunctions. So one way you can do this, it's really hard for me to do it on the projector, but I can do it on the whiteboard pretty quickly. One way to look at this is you have an OR, and then the OR has two operands. One side of the operand is an AND, the other end is also an AND. And then the first AND has a negation of A and the non-negated version of B. The other one has the non-negated version of A and the negated version of B. So when you look at it this way, sometimes it's easier because it just kind of graphically shows you the hierarchy of the operators. So I'm sorry I cannot do this on the whiteboard, not as quickly. But it's easy on the whiteboard. All right. Okay, so now that we know that expression, making use only of the not, and ors can express X exclusive or B, we can just do a literal translation, right? Every time we need a not, we'll just stick that gate over there. Every time we have an and, we stick the other clunk of gates. And then every time we have an or, we substitute with the other clunk of gates. It would not be an optimal design, okay, but it will do it. Okay. So as far as this class is concerned, we just have to say, yes, it is possible, we can do it. All right, that's a good question, I like it. All right, so this part is now done, and we are moving on to analog versus digital. Almost all computers today are digital computers. In other words, we don't really go between the 0 and the 1. Okay, the voltage or the state of a transistor is either on or off. There's nothing in between. And the reason why we like computers like that, being digital or only have one or the other state, is because this is easy to duplicate stuff, to do computation, and to deal with noise. Is that making any sense or not? Think about a CD-ROM, okay? Think about a CD-ROM. What do you think, if you put a CD-ROM under magnification, what do you see? It's a mirror with holes, right? Okay. So if you magnify a track on a CD-ROM under a magnifying glass, you basically end up with holes like that, and these holes versus no holes will basically be representing zeros and ones. Okay. So it's either the presence of a hole or the absence of a hole. We don't really care about the actual size of a hole. They can be off by 5%. You know what? It still registers as a hole, okay? It's not a problem. But why is that advantageous when it comes to time to duplicate a CD-ROM? Okay, go ahead.
Well, when you duplicate, and then if you're duplicating off of the duplicate, the errors get larger and larger each time. So
if it is analog.
Yeah.
Only if it's analog, where the size of a hole really matters, then if every time you have a 1% error, then the copy of a copy will have above 2%, the copy of a copy of a copy will have about 3%, and so on. So that is absolutely the reason. Okay, that's good. Okay, that's the reason why analog stuff is not as good. Most of you are too young to remember analog stuff, like cassette tape and stuff like that. Okay, cassette tape, LPs, okay, vinyl, okay. Those things are notorious for making copies because of the errors that you introduce every single time you make a copy. So a copy is worse than the original. A copy of a copy is doubly worse than the original, and so on. But if it's digital, it's easy because I only need to know whether there is a hole here or not. So the duplicate only also needs to have a hole or not. The size of the hole doesn't really matter as long as it is still within tolerance. Is that okay? All right. So that's why most computers or all computers today are digital instead of analog, because it just makes the components much more noise immune, and you don't need to select components to make sure that everything is in high fidelity. Because if everything is analog, you have to match the transistors so that when one is half on, the other one is exactly half on. And it's really hard to trim transistors so that they match up exactly. If you are an audiophile, you probably will understand the importance of matching components. With digital stuff, there's no matching. It either works or not. So that basically just explains why we have digital computers and gates. If there's one sentence you want to use to remember what digital is all about, it's this one here. There's no dimmer. The light is either on or off. So gates is something that we have just talked about, and this is the source of another page. If you want to, you can go there, but it basically just kind of duplicates, well, I actually borrowed, concepts from this slide here to talk about how to make a gate out of transistors. All right. So now we move on to, from transistors, we get to logic gates. From logic gates, now we get to values, numbers, and how we represent numbers. We look at this picture here, and we ask, how many samurais are there?
7.
Okay, are you sure? I think there are 111 in base 2 samurais. I can also claim, okay, so there are I can say this is 111 in base 2. I can say this is 21 in base 3. I can say this is 13 in base 4. I can say this is 12 in base 5. And I can say this is 11 in base 6. Okay? So what is going on here? This is the same quantity that we normally associate with this symbol, 7. Okay? So how can the same quantity have different names, like 111 in base 2, 21 in base 3, and so on? Is that a problem? It's not a problem. So to make sure that we understand the difference between what we are trying to represent and the representation, the symbolic representation itself, I have this. Okay? And this is normally associated with which emotion?
Oh.
Most people will say happy, but you can also say medicated if you want to. Okay. So let's say it's happy. Okay. So what exactly is happy? It's an emotion, right? When I say happy, when I spell out happy, H-A-P-P-Y, it becomes just symbols, sounds, to represent the actual emotion. Is that making any sense? And the reason why we have the word happy is for communication, so that I can tell you, oh, this face usually represents that particular emotion. And through education and language learning, you would understand, oh, okay, happy means that, and this is how we communicate. So the same face or the same emotion, you can write it in Chinese, you can write it in Russian. Now, I only did a Google search or Google Translate in this case, so if it is off a little bit, please forgive me, okay? You can write it in Japanese, you can write it in Vietnamese, or you can write it in Spanish. But all of those are nothing more than symbolic stuff to represent an emotion. And emotion cannot be expressed on a piece of paper, right? I mean, it's not the paper that is emotion, that is the emotion. It's what it is representing. Are we doing okay so far with this analogy? Because we are going to go back and talk about numbers in different bases. So in this case, a value, a quantity, is kind of like a mood, an emotion. It can be described by different numbers, and each number is basically just a word, a translation, a symbolic thing to represent the quantity. And that's why now we can use different bases. Okay? Base 10 is just handy because we got 10 fingers. Okay? If we had only 8 fingers, it would have been octo. So octopus, being really smart animals, probably communicate in base 8. And insects, probably count in what? Base 6, because they only got 6 legs. Yep.
So when we change the bases, we always move to the next exponent each time we reach that base. So like if we have
Right. Exactly. It's because the number of alternatives per position in the number is the base that you're dealing with. So in base 10, we have 0 to 9 to make up the 9 symbols per position. And that's why with a single digit, we can never represent the value of the base itself. So base 10, in base 10, 10 as a value, as a quantity, cannot be represented by a single digit. It needs 2 to get to. All right. In a digital computer, it makes sense to use base 2 because everything, all the transistors, are either on or off. Okay, and base 2 is really the same thing. Okay, 0 or 1. So you just have to pick, low voltage or off being 0, and high voltage or on being 1. Okay, and that's it. That's a direct translation from a physical quantity to a digit, to the value of a digit. And then I just did another conversion here, and it's the same thing that we did a little bit earlier, so I'm going to skip it. And that's the end of this slide, I think. Yep, there we go. All right, so with this one covered, we can now go back to the other one, which is it's in another browser right here. It's the same thing. This is just a part that explains how we read a number. 1742, 1742, we break it up into the components, and in each component we specify the quantity and then a power of 10 instead of power of 2 in this case. So stuff that we have already talked about, we'll kind of skip through this. This is the same thing, it's the reverse. So if I give you a binary number, how do you convert it back into a base 10 representation? It's just the reverse of what we did earlier. Okay. So with this one, it's easier for me to just point it out. This digit tells you how many ones we have. So we have 0 ones in this case. The next one tells you how many 2s we have, how many 4s, how many 8s, how many 16s, and how many 32s. So if you just kind of add up the quantity of those powers of 2, you get the quantity back. So are there any questions about how we read a binary number and get back to the quantity that it is representing? Questions? Okay, all right. There are no questions about this one. Then we'll move on. And the next slide talks about adding in binary. Okay, in base 2, how do we add? Now before we do base 2 adding, let's go back to base 10 adding, just so that we know what it means to add something, right? So I'll start with something like 3 plus 8 in base 10. Okay, this is all in base 10. What is the answer?
1, 1.
Okay, it's 1, 1. But the way I write that 1, 1 is going to be, it has a sum of 1 and a carry of 1. Now the reason why I do not write it out as 11, 1, 1, right next to each other, is because if I do it this way, I can do multi-digit addition. Does that make any sense? Okay. And by the way, how do you know 3 plus 8 is 1 with a carry of 1? Why? Okay, but I didn't see anyone actually counting. So how did you get to this answer?
Well, because we surpassed 10, and so we have to carry it over to the next place number.
It's because you have memorized. Because you have memorized all this stuff since what? Second grade, third grade, or something like that? Okay. But how many things did you have to remember?
10.
No, it's a little more than that.
You know the repeating of it all.
Oh, yeah,
I mean,
well,
you only know 10
right.
different characters.
Well, technically speaking, we have up to 10 digits here and 10 digits here. So the table really is a 10 by 10 or 100 entry table. But we know half of it is duplicates, so we'll have it to become like 50 entries. And of the 50 entries, some are easy, like 0 plus whatever is just whatever, right? But you still have to remember quite a bit. How many people have either a younger sibling or a son or daughter in second grade or so? Okay, do they learn this stuff like overnight? Like one day the teacher talks about, oh, this is addition and this is carrying, and the next day they can carry out like 6-digit addition with no problems. It takes time, right? It takes time to remember all of these things because there's no other way to do it other than memorization. Great. Now let's think about binary addition. Binary addition is easy. Easy schmeezy. All of that stuff is in the document already, so I'm not too concerned about you writing on the whiteboard. 0 plus 0 in base 2 is what?
0.
So the base doesn't really matter. 1 plus 0. Oh, do we have a carry here? No. Okay, if there's no carry, I'm going to say there's a carry of 0. Okay, works out the same way. It just sounds kind of redundant, but it is not. 1 plus 0 is 1. Even in base 2?
Yes.
Okay. Does it have a carry?
Yes.
It has a carry of 0. Okay. Well, same thing. 0 plus 1 in base 2. 1 in base 2. Okay. Does it have a carry? There's a carry of 0. Okay. So we only have 1 left, right? 1 plus 1 in base 2.
0.
It has a 0 with a carry of 1. That's all you have to remember. Of the 4 that you have to remember, the first 3 are trivial. So there's only one thing that is quote unquote special, which is 1 plus 1 is a 0 with a carry of 1. Don't tell your kid this is how binary numbers work, because your kid will go back to school and say, teacher, why are we using base 10? It makes sense, right? I mean, it really makes sense to teach binary numbers because it is easy. It really is a whole lot easier than base 10.
When you're dealing with small numbers anyway.
Well, that's why we have hexadecimal numbers when we deal with large numbers. We'll get to that part too.
See,
Okay.
that's difficult for kids with only 10 fingers.
You're taking your shoes off in middle class.
Kids these days, they only have 10 fingers, but they also have mobile devices.
How to get the 0 there?
Sorry?
How to get the 0 there?
How do we get the 0 here? Because the quantity represented by of 2 cannot be represented by a single digit in base 2. In base 2, you only got 2 alternatives per place in a number, 0 and 1. Well, how are we going to represent the quantity of 2 using only 0s and 1s? Well, we'll put a 0 here and move on to the next place. Remember, this place is the number of 1s, the next place is the number of 2s, and the next one is the number of 4s, number of 8s, and so on. Okay. So are there any other questions about binary addition? Well, since we're talking about all this stuff here, let's deal with subtraction. It has to be a lot harder, right? Let's try it. 0 minus 0 is 0 with a borrow of 0. Okay. 1 minus 0 is 1 with a borrow of. I'll skip this one. 1 minus 1 is 0 with a borrow of 0. Ha! This one has to be hard, right? 0 minus 1 is, okay, I don't want to deal with this in base 2. Let's think about it in base 10 first. 0 minus 1 in base 10 is?
-1.
You can call it -1, but if I want to perform multi-digit subtraction, how would you call that? No, it's a 9 with a borrow of 1. Right? Because I run out of stuff from this digit already, so I'm just going to go to the next digit and say, hey, give me 1. Right? That's the borrow. So getting back to this one, what do you say when we subtract 1 from a 0 in base 2? We have to borrow 1 from the next digit, but the 1 borrowed from the next digit is a 2. 2 minus 1 is 1. That's right. So the answer is the difference is 1 with a borrow of 1. And that's it. 4 rules for subtraction, 4 rules for addition. We are all set.
You want to do a multi one? Would you like to do a multi one?
Let's go ahead and do a multi-digit. Do you want to do subtraction or addition first?
Subtraction.
Subtraction? Well, let's do addition first, and then we'll do the subtraction, okay? You guys can give me, okay, how about this? You give me a number in base 10, we'll do the conversion first, and then we'll do the binary addition and the binary subtraction. How's that? Just don't give me something that's really big, because it's just going to take a long time. 255 is interesting because if you subtract anything from 255, it will never trigger a borrow, so it's not really a whole lot of fun. No?
Do you want to stay within a byte?
Within a byte would be good, otherwise it would just be time consuming.
148.
14 minus 11. 14 minus 11.
14 minus 11 for 4 bits, that's easy to work with. Okay, very good. So we want 14 in base 10 minus 11 in base 10, but I don't want to do it in base 10. I want to do everything in base 2. So the first thing we have to do is to convert it into base 2 first. 14 in base 2. Okay, so you have to re-express 14 in powers of 2. Okay, if I want to do it step by step, you have to do it in powers of 2. I cannot start with 16 because 16 is greater than 14 already. So the largest power of 2 that is less than or equal to 14 is 8. So we have 8. Once we take care of the 8, we have 6 left. So the next one is going to be a 4. Once we take care of the 4, we have 2 left. So it would be 8 plus 4 plus 2. And then you convert these into actual binary numbers. And this becomes 1000 in base 2, the 8. The 4 is 100.
No, 1010101.
Right, but I'm not writing the leading zeros.
Okay, well then 10.
So the one more zeros here. Yeah, wait.
Yeah, because if you want to do it in 4
No,
bytes,
no,
yeah,
no,
you're
no.
going to stay in 4 bits.
No. This is fine, right? Because it's 2 to the power of 2, so we have 2 zeros. And then the 2 is 10 in base 2. So we now add up all of these things, and it becomes 1110 in base 2. Okay. 11 is going to be 8 plus 2 plus 1. So it is 1000 in base 2 plus 10 in base 2 plus 1 in base 2. So it boils down to 1011 in base 2. Okay. And then the next thing we want to do is to do the, let's do the subtraction first. Okay.
But there will be no borrow in this one.
There's no borrow? There's borrow.
Oh, yeah, with the borrow.
The first digit, the least significant digit, has a borrow already. So 1110 in base 2 minus 1011 in base 2. Let's see how we can do it. 0 minus 1 is a 1 with a borrow. Okay? 1 minus 1 is a 0. 0 minus 1 is a 1 with a borrow. 1 minus 0 is 1. 1 minus 1 is a 0. 1 minus 1 is a 0, and there's no borrow from the previous digit, so this is just a 0 here. So the result is 0011 in base 2. 11 in base 2 is 3. Does it make sense? Yep. Sorry? 1, 1 is 3, yes, because we have 1 of 1 and 1 of 2.
How evil is 10 base converted minus base and base and then just converted is that's really.
She's saying it doesn't matter because it converts itself.
If I do 10 base, which is 14 minus 11 is 3, and I convert to 3, it's just 1 1.
So do the subtraction first and then convert?
Base 10 and then go back.
If you do the subtraction first in base 10, it will come to the same answer,
Yeah.
because the quantity of 14 minus the quantity of 11 is always the quantity of 3. Okay, so the quantity does not change. But what I'm really trying to do is to illustrate how to do it in base 2. Okay. Yep.
Why are we carrying 1 when we can 0 minus 1 in base 2?
It's not a carry, it's a borrow.
What do you mean by that again? Just real quick.
Because we're dealing with subtraction,
Okay.
so we're dealing with a borrow. 0 minus 1 is 1 with a borrow from the next digit. It's kind of like, in base 10, if you have base 10, if you have 100 minus, I don't know, 14, okay? What is it? 0 minus 4 is 6 with a borrow. And then 0 minus 1 is 9 with a borrow. 9 minus 1 is 8. 1 minus 0 is a 1. 1 minus 1 is a 0. Well, that's the way I write it. I know some of you may not write the same thing, when you have borrows, but you guys, basically, it's the same idea. It's just that in base 2, 0 minus 1 triggers a borrow.
0 becomes a 2, basically.
Say again?
0 becomes a 2 if it's taking X number over.
Right. You're basically saying, okay, I don't have enough quantity in this digit. I'm going to borrow 1 from the next digit.
Yeah.
Yep. All right. So, question?
Borrow 1 from that side. Wouldn't it be 0 then? No. Well, you're doing, never mind. Got it.
No, it becomes
Yeah,
a
it's
2 and then
subtraction,
minus 1
yeah.
and it becomes a 1.
Yep.
Yeah.
It follows the same rules, exactly the same rules as base 10 subtraction, except when you have 0 minus 1, it has a difference of 1 with a borrow. That's the only exception that you have to deal with when you try to reapply what you have already learned with base 10 subtraction. Okay, well, let's go ahead and try addition, because this only illustrates subtraction works. Let's try addition. And what is better as an example than reversing this, right? We are adding this number, the difference, back to the number that we're subtracting from.
So we should get 14.
So we should get 14 back, or 1, 1, 1, 0 back. Okay, so let's do the addition here. 1 plus 1 is a 0 with a carry. Okay, 1 plus 1 is a 0 with a carry, and then 0 plus 1 is a 1. 0 plus 0 is a 0. 0 plus 1 is a 1. 1 plus 0 is a 1. There's no carry from the previous one or a carry of 0. So 1 plus 0 again is a 1. So we have 1, 1, 1, 0 back, which matches this one, which is also 14. All right. Yep, go ahead.
I don't know if this is the same thing, but if it's too much. But so, like the processor that carries this, it has like a register for the carry bit, or like will it carry? Does the register maintain both a carry and a borrow?
We'll get to that part. We will get to that part. But first of all, we want to be comfortable with binary addition and binary subtraction, because everything inside the processor happens in binary. Okay, they're all zeros and ones, and transistors. Okay, that's the important part, because at this point we have a little bit of a disconnect, because we spent the last class talking about transistors. Okay, N-channel MOSFET, P-channel MOSFET, and stuff like that. We spent the earlier part of today's class talking about gates, right? We talked about the NAND gate, how we can use 4 transistors to implement a NAND 2 gate. And then we suddenly jump to quantities and the representation of quantities using base 2 numbers. And we talked about the rules of addition and subtraction in binary. There's no connection between those things, okay? Because we got calculations, values, quantities on one side, we have transistors and gates on the other side. So how do we get a computer which is made out of transistors and gates as a higher level construct to perform calculations? That's the missing link here, okay? Well, let's take a look at the missing link and see if we can figure it out. When you look at this particular, let's just focus on addition, okay? When you look at addition, how many independent inputs are we dealing with? Two independent inputs, very good. Okay, so we are dealing with bit X plus bit Y. How many outputs are we dealing with here? We have, well, kind of two outputs, because we have the sum and then we have the carry. Okay? Is that okay so far? So all the additions that we ever have to perform can be expressed by using two inputs and two outputs. Okay, let's write out that table. X, Y are independent variables. The sum is a result that we want to be a certain value depending on what X is and what Y is. And then the same thing with carry. Those two are outputs. So we'll just go ahead and draw out this little table here. X and Y are independent, which means when X is 0, Y can be 0 or 1. When X is 1, Y can be 0 or 1. Is that okay so far? So that will help us set up the input to the I call it the half adder. Okay, this is the output of a half adder, and there's a reason why it's called a half adder and not a full adder. What about the sum? 0 plus 0 has a sum of 0, and a carry of 0. 0 plus 1 has a sum of 1 and a carry of 0. Okay? 1 plus 0 has a sum of 1 and a carry of 0. And x plus y, 1 plus 1 is a 0 with a carry of 1. Okay. These two are inputs, so I just want to re-emphasize this is the input into the system. This is an output, and so is this. The two outputs, you can kind of look at those as independent things. They're not really related to each other. Okay. Okay. When I look at this table here, even though it is describing the rules of addition in binary, at the same time, it kind of looks like a truth table. Right? We have a whole bunch of zeros and ones. That makes it kind of a truth table. Let's see if we can identify something in this truth table here. Both inputs being 0, the output is 0. If we have at least one 0 in the input, the output is still a 0. The only time we have the output being 1 is when both inputs are 1s. Do we have a convenient way to express this? It's just and. Wow. Okay. So the carry of X and Y as individual bits is really just X and Y. That's kind of convenient. What about the sum? Well, in the notes I use R for result. Okay. So what about the sum here? The result of X and Y being individual bits. I think we have just seen this before. Somebody asked me about something, and we came up with a truth table that has exactly this pattern. What was it? Exclusive OR. Okay, and exclusive OR has this representation in mathematics.
What was the R again?
R is result, which is basically of the sum. I just did not use the symbols consistently here. Okay. Was I talking about the missing link a little bit earlier? That we had quantities, numbers, binary representation, binary addition, binary subtraction on one side, and we have transistors, gates, and electrical signals on the other hand. That's the connection. Binary addition, the rules of binary addition can be implemented using an AND gate here and an exclusive here. Now we have just shown a little bit early in today's class that exclusive OR itself can be expressed using only negation, conjunction, and disjunction. And those, in return, can translate to NAND gates. So everything that we have here can translate to NAND gates. And NAND gates can be implemented by switches, transistors, relays, vacuum tubes. So now we have the entire connection, right? At the lowest level, we have transistors, we have wires and stuff like that, physical quantities, high voltage, low voltage. This transistor is on, that transistor is off. All of that stuff will translate into logic gates because it's a high-level construct, it's a more abstract construct. And then on the other side, we start with the representation of quantities. 14 can be translated into 1110. We talked about the rules of addition and subtraction in binary. And here, we can see that they meet in the middle. Are we doing okay so far with this kind of bigger picture? The detail is kind of involved, okay? But the most important part is the big picture. Are we still doing okay so far? So that means we can now implement a half adder that can really do phase 2 addition using only logic gates. Is that okay? So let's take a look at how we work this out. Okay, and I'm gonna, I'm gonna do this using Logic Sim. Okay, because I just want to help you guys, understand how to make that tool work. And it's a pretty useful tool, pretty easy to work with. So jar Logic Sim. Oh, okay. Even though everything is running out of a external hard drive connected by USB 2.0, it still runs a whole lot faster than in Windows that is on the installed internal drive. In case you guys haven't noticed. Nah, you guys know. Okay. All right, so we'll go ahead and implement this stuff here. Okay, 2 input bits, one as the result, which is the sum, and one as the carry. So we'll try to implement all of that stuff, not using NAND gates because that's just going to be really tedious. So we'll go ahead and use the exclusive OR gate and also the AND gate. Okay, so we'll make life a little bit easier for ourselves. All right, so we'll start with wiring and pick out some pins. So we'll pick out the first input pin, duplicate, make it the second pin. This time I will be nice and actually label the pins. So this is pin Y, which is on the outside, and this is pin X, which is the other input. So each pin is representing 1 bit as the input to this calculation thing. We'll go ahead and pick out 2 output pins. Okay, so we'll pick out 1 output pin here and 1 output pin here, and we have to do 3 things. Sorry. We'll change the facing so that it will be facing west. It's just easier this way to make connections. And then we also have to change the output from no to yes. Okay, so now they are both output pins. And we'll go ahead and label this. It doesn't really matter which one I pick as the result and which one is the carry. I'll just pick this one as the result, and I'll pick this one as the carry. And by the way, you can also change where the label appears by changing label location. Yep. So we want it to be on the other side, just so that it looks a little bit nicer, like that. Okay. And to make it even easier to read, I just want to zoom in. Right. Well, the 2 outputs are independent. Okay. So what we'll do is we'll implement the easy one first. Okay, the carry is the easy one. It's just an AND gate, right? So we'll go ahead and specify the AND gate. So we go to gates here and go to AND. We pick out an AND gate, and the default AND gate has 5 inputs and is really big. So we'll just go ahead and change the gate size to narrow, and we'll change the number of inputs to 2. And now we have our usual AND gate. draw a line from here to the second input, and draw a line here to the first input. And the output out of this AND gate is our carry already. It's done. Okay. The next one we want to specify is the exclusive OR. Now I know we can just use an XOR, exclusive OR gate. Let's go ahead and do it in a slightly more difficult way. Not quite all the way down to NAND, but using just AND, OR, and NOT. Okay. Okay. This one is actually not too bad because you can use two. Okay, I don't want to do this. Escape. Okay. So what I'm going to do is to duplicate this one. So you select it and you press Control D to duplicate it. So I'm going to duplicate it twice. Now with an AND gate, it gives you a really nice option. You can choose to invert one or both of the inputs. Okay. So that is really handy because exclusive OR, okay, I just want to remind you guys, exclusive OR is basically the same thing as not X and Y, or Y and, oops.
X and not Y.
Yep, X and not Y. X and not Y. So when you look at this AND gate, one of the input is negated. When you look at this AND gate, the other input is negated. And then the output of both of the AND gates will go to the OR gate, and then the output of the OR gate becomes our result, which is the sum. Okay? So that's why I picked out two AND gates here. With this one, I'm going to invert or negate the first input, and you can see that negation is represented by a circle. And with the other one, I would negate the second input, like so. And now it's really just a matter of drawing lines. Yeah, we can just go from here. There we go. And then from this guy, we go here, and from here to here. Okay. Sorry?
What does that circle do again?
This is a circle means negation.
Oh, okay.
So I'm negating the input to the gate in this case.
Okay.
So that I don't have to use an explicit NOT gate.
Yeah.
Because it takes up room and it doesn't look nice. Okay, now we have these two outputs out of the AND gates, and they have to be going into a OR gate. So we specify a OR gate, and we'll specify a narrow one with only two inputs. So we take the output of the first AND gate into the first input, the output of the second AND gate into the second input, and then we just hook all of these to the result, and we have what we call a half adder. Now it is only called a half adder because in order to finish one column in binary addition, we need two of these things. Okay, we won't have enough time today to finish that. But what we do want to do is to say, well, does that really implement this? Okay, that we can do today. We want to verify that this particular schematic of gates is going to implement a half adder the way we specify here in the truth table. Okay, so it's time to turn this into simulation mode. Okay. When it's in simulation mode, we can now specify 0 plus 0. So what this is really saying is 0 plus 0 has a result or sum of 0 and a carry of 0. Okay, that seems to work out. The next one is turning y into a 1. And you can see that the result is a 1, and the carry remains as a 0. Still working. Let's go ahead and flip the 0 and the 1s. So x gets 1 and y gets 0. The result is 1 and the carry is 0. Is that correct? Everything seems to be working. And the last one is y being a 1 as well. And this is the only time when the carry is a 1, but the result should be, or the sum should be a 0. It all works out, right? So what if I were to tell you that this is only 1/2 of adding 1 bit, and I want you to make a 16-bit adder? And you go like, no, no, right? Well, logic sim is really cool in a certain way because whatever you can draw here, you can turn it into a library part. Now, once it becomes a library part, it's kind of like a class. And when you have a class, what do you do with the class? Stamp out instances, right? So you can stamp out instances, but I wouldn't stamp out 32 instances to make a 16-bit full adder. I'll stamp out 2 to make one full adder first, and then I'll stamp out 16 of the full adders to become a 16-bit adder. So that's something that we'll do next Tuesday, but you guys can try to do it ahead of me, okay? It's kind of fun. And I'll give you just one last clue of how to do that. So you want to go to project and you say add circuit. And you'll just give it a name. So in this case, we'll call this a half adder, okay, HA. And you can see now that we have half adder. Whatever the magnifying glass is on is what is being displayed here. So if I switch back to main, uh-oh, where is that? Okay, I guess I need to zoom out. Uh-oh. What happened to my...
If you double click on it?
Oh, double click. Thank you. Yeah, it's double click. There we go. So we still have it here. And so what we'll do is to copy and paste this because half adder is currently empty. There's nothing here. So we go back to main and then we select. It's really just select. It's drag and make it include everything. If you're worried that you might do the wrong click and accidentally delete the whole thing, just do a copy. Instead of cut, do a copy. Go to HA and paste it. Okay? So now we have a component called an HA, a half adder. And then you go back to main and say, okay, we don't need this anymore because it is now a component. So every time you want to instantiate to make a half adder in the main circuit, you just click HA, and that will make a little component that really is just a half adder. This is an instance of a half adder. So this is an object, whereas when you double click on HA, it shows you the definition of the quote-unquote class. Okay, to borrow terminology from your other classes. And it's nice because it makes abstraction easy. You can build tiny, small components first, then you build larger ones, and then you can build larger ones and then larger ones. Because there's no limitation of how many times you can stack abstraction. So you can make a full adder using 2 of these things and an extra gate, turn it into a component, and then make more instances of that.
So as you said, so a half adder can only do addition for single bits, like for basically numbers.
2 half adders can do 1 column of binary addition.
Which 1 column, which is just 1 bit, right?
Yes, 1 column is 1 bit. Okay. So that's why it's called a half adder, because it doesn't quite do the entire addition. Okay. Because I can just kind of illustrate real quick here. What I mean by half adding, because when you're adding in binary, which is here, okay, there's one. Let me use a different color. There's 1 addition here. 1 plus 1 is 1 addition. There is an implicit carry from the least significant digit.
Yeah.
So whatever the sum of these 2 bits are, that's red too. Okay, but the sum out of these 2, you need to add it to the carry from the previous digit. That's the second half adding. So the result from the second adding becomes the actual result here. But both of these can contribute to this particular carry of the next digit. So in the next class, we'll talk about how to make a full adder out of 2 half adders. And once we know how to do 1 full adder, the other ones are pretty easy, because you have 2 inputs from the numbers themselves and then 1 extra input, which is the carry from the less significant digit from the previous one.
So we're going to go over half adding in the next class too.
The half adding is kind of done. It's also in the notes, so that part is kind of done. So next class we'll talk about fold adding. Next Tuesday we'll talk about fold adding. And in today's lab, I scheduled activities already. In today's lab, we'll talk about how to use the Linux toolchain. Now, we haven't really gotten started with assembly language programming, so I'm not going to use that as an example. Instead, I'll use C programs as an example. The focus is how to work with the command line interface, how to compile, what compiling really means, how to link, and how to use GDB. Now, using GDB is the big one, okay? It will take some time to get used to it, but once you get used to GDB, it is a very, very useful tool to help you debug your programs, okay? Just remember one thing, we won't get to printing something on the screen for a long, long time, so do not rely on printf or cout for debugging. Yep. All right, so you guys can take a little break, about 5-10 minutes, and I'll be in room 126. Okay. Yep. So what exactly?